Muy buenos días con todas y todos los que nos acompañan esta mañana. Les agradeceremos mantengan por favor apagados sus micrófonos y cámaras durante el transcurso del webinar. Bien, vamos a dar inicio al webinar Proyecciones mecanísticas para las poblaciones de sardina y anchoveta en la Corriente de California basadas en modelos oceánicos regionales a cargo del doctor Stefan Koenigstein. A continuación, tenemos las palabras de bienvenida y presentación del expositor de la mañana de hoy, a cargo del doctor Dimitri Gutiérrez, director general de Investigaciones Oceanográficas y Cambio Climático del MARPE.
Bien, muy buenos días con todos. Es un placer el día de hoy tener como invitado al doctor Stefan Koenigstein. El doctor Koenigstein realizó sus estudios de doctorado y maestría en la Universidad de Bremen, Alemania, y es ingeniero ambiental de la Universidad de Ciencias Aplicadas de Bremen. Él estudia los impactos del cambio climático en el ecosistema marino y las pesquerías, usando modelos como herramientas integrativas para entender mejor la respuesta del ecosistema. Él actualmente se ha desarrollado como científico en la Universidad de Santa Cruz, California, y la NOAA, específicamente en la NOAA Southwest Fisheries Science Center, trabajando en modelos dinámicos de población integrativos de peces en la Corriente de California, en el marco del proyecto Future Seas 2.0. Su trabajo se centró en la incorporación de los procesos biológicos y la evaluación de la incertidumbre en estos procesos. Se encuentra mejorando la interrelación de los modelos y los datos observacionales y experimentales con el fin de permitir entender los múltiples estresores ambientales bajo el cambio climático y proveer apoyo al manejo de los recursos. Previamente, el doctor Koenigstein también ha trabajado en proyectos interdisciplinarios de investigación entre Noruega y Perú, conectando la ecología marina a las pesquerías. Adicionalmente, ha desarrollado técnicas educacionales para nivel escolar y grupos de educación ambiental que permite entender el sistema oceánico y sus usuarios. Entonces, con esto estaría dando paso a nuestro expositor, cuya presentación será dada en idioma inglés. Los slides están en español y para las preguntas y respuestas el doctor Koenigstein procurará darlas en español, a no ser que hubiese alguna dificultad donde nosotros podremos apoyar, digamos, a la traducción en ese instante. Stefan, welcome for this webinar, and well, the floor is yours. Thank you very much.
Muchas gracias, Dimitri. Gracias por la invitación. Hablo español, pero me falta un poco de práctica, así que voy a dar el talk en inglés. As has been said, I work on mechanistic population projections in the California Current for Pacific sardine and northern anchovy. And I work on integrating ocean models and other data into those population models. And I'm based at University of California and NOAA Southwest Fisheries Science Center. As I'm sure you all know, small pelagic fish are among the most variable fish stocks in the world. They're famous for their boom and bust cycles, but the reasons for the cycles are still not really understood. In the California Current especially, there's been a classic picture that sardine and anchovy are kind of alternating in the last few decades, as you can see at the bottom left. And there have been attempts to link the productivity of both populations to either large-scale climate indices like PDO or to sea surface temperature. But the attempts to consider sea surface temperature for sardine, for example, for sardine recruitment, it has been statistically significant, has been incorporated into the harvest control rule, but it hasn't really held up so far. And further problem is that the correlation with large-scale indices like PDO, where we don't really have a mechanistic basis, we don't really know what the reason for for the correlation is we have no information about how certain it is that they hold into the future when ecological conditions are changing and physical conditions are changing. And especially in the California Current, we've had a very strong heat wave in the years 2014 to 16, followed by El Nino, and with very warm surface temperatures. That's a screenshot in the middle, the bottom middle part. But contrary to expectations, as the classical picture has been that sardine does well in warm years and anchovy in cooler years. But we've seen the opposite in the last few years. The sardine has not recovered, but has stayed low and stayed collapsed and is not being fished. But anchovy has increased in the last few years after that, which illustrates that we haven't really understood what's going on. On the other hand, the global and regional ocean models and plankton models, biogeochemical models, have improved a lot. But we haven't really been able to use those for modeling the variability in fish stocks. I'm still on the first slide, sorry. We haven't really been able to use those for the population models because we don't really have a full understanding of how the population dynamics are linked to the environmental and ecological drivers. So now on that slide. This is why I've worked on developing a model, which is the slide. The model I've developed is an age-structured population model for sardine and anchovy, and you could call it a model of intermediate complexity or a MICE, which means that basically the idea is to have just the complexity that's right to assess system dynamics and the question of interest. So it incorporates everything a little bit, but nothing really in full detail. So I'm using data from different areas. I'm using stock assessment data, so that's biomass at age and landings at age. I'm using spatial fisheries survey data and plankton survey data. So that's the Calcoffee survey in California gives a lot of data on eggs and larvae distribution in the California Current, and there's acoustic trawl surveys giving data on distribution of adult fish. And then I'm using the input from ocean models, from regional ocean models, downscaled ocean models, and plankton models for the spatial and temporal dynamics of those parameters. And I'm trying to integrate all these different aspects to look at what drives system behavior and feedbacks, and to use that for projections. So you can see the structure at the bottom left in this scheme. You can see there's the different life stages. There's larvae, there's juveniles, and these go into adults, and the adults have an egg production that goes back into eggs and larvae. And the early life stages are impacted by temperature, which impacts the development and the thermal mortality of the early life stages, and by offshore transport when they're advected offshore. Then the later life stages, when they start feeding, the feeding larvae and juveniles impacted by food availability. The adults are also impacted on food availability, and this consumption impacts their egg production. And they're also impacted by predation and by fisheries mortality. And so the model, these are the different drivers that the model is integrating. And then to the right, you can see the map. So I have a kind of reduced spatial resolution. There you have 24 cells in the California Current. And this integrates the output from hindcast and downscale projections from ROM's biogeochemical model. The Nomura model that's been developed at UCSC has three zooplankton and 2 phytoplankton compartments. Próximo slide, por favor. No, el de antes. Hay otra parte en este. Okay, no importa. So there's spatial processes. On this grid, I kind of move the feeding and the spawning habitat of the population. And the spawning habitat is determined by the sea surface temperature, which is kind of fitted into the model before we fitting the population model. And then the offshore transport is determined by upwelling strength. I use an index that's called QT that's been developed by Mike Jaycox to give an index of upwelling strength to determine offshore transport of the larvae. And then the assumption is that the feeding migration of the adults follows the location of the best food, and there's different maximum feeding distances. I will explain that a bit more. Proxima slide. So this model was fitted to data from the stock assessment, the age-structured data from in the period from 1980 to 2010, fitting the numbers at age and the landings at age, and as I said, the Calcophe egg and larvae data for the location of the spawning habitat. And then I run a lot of sensitivity analysis and to have a wide parameter search to look for all different combinations of parameters that explain the historical trajectory of the biomass at age during the fitting period. This is driven by the hindcast and in the ROMS biogeochemical model. And then I made a selection of like 300 different fitting models, and then I further optimized those. And then I picked 9 models that are representative for the whole range and for the parameters, the different parameters that have the same explanation. So there are basically 9 different explanations for almost the same biomass trajectory. And you can see that here in total numbers gives a fit between 0.73 and 0.R5 and ask value. This is to 2010, and then I do a testing of the model after 2000, from 2011 to 2018. And I was assuming low food here, then testing the model, and it actually I'm assuming low food even with high temperature and no fishing, but assuming this low food, this explains why this possible explanation why the biomass is still low in the sardine stock. Proxima slide. So this is the fitted model, and the fitted model is then projected into the future. There are 3 different Earth system models. This is the GFDL, the Hadley, and the IPSL model. And as I said before, I'm using SST, upwelling strength, and the different plankton compartments from these models. And this is under a business as usual emission scenario, RPC RCP 8.5. And the models kind of represent different warming rates. So they're meant to have the range of possible futures. So to say, the GFDL model has a relatively low warming, and the Hadley and IPSL have a faster warming. And there are different changes in upwelling and plankton too. Yeah, you can see again to the bottom left fit to during the calibration period. So this is the range of the 9 different model configurations. And then there's an additional small challenge if you want to forecast into the future, because these models have temperatures that are behind the historical period. So if we want to extrapolate into the future, we have the problem that we don't have any information in the past about what these high temperatures caused. So what I'm doing to solve that problem is a sensitivity analysis, which can be seen in the small graph to the right. The black dots are the fitted part, and the red and blue is basically my low and my high assumption. I have more on that on the next slide. Proxima slide, por favor. Yeah, so these are the thermal curves. This is for survival of the egg and larval stages among the 9 different model configurations. And you can see that the fitting data is the same. The steepness and curve changes because the plankton effect in the model is also different. And then the blue line just gives like, okay, let's assume the optimum, the thermal optimum for the life stages is pretty low. So it's kind of a 15, a little bit above 15 degrees. And the red line gives the highest possible thermal optimum. So this assumes we don't reach the optimum in the future, that just keep on growing better, and temperature has a positive effect still in the future. And it goes up to beyond 17, which is beyond the whole range of temperatures we have in the projection. So the correlation is positive for all the different configurations, but to different degrees. Próximo slide, por favor. This more detail on that. You don't have to look at every detail on this. Just this is for the 3 different models. The range, the colored range is the range of thermal uncertainty for the different model configurations and the different columns, the 1 to 9. You can see 2 things. First thing is that in the faster warming models, obviously in the Hadley and IPSL, the thermal uncertainty is bigger because there's just more warming, there's more change in temperature. In the GFDL, it doesn't play such a big role. And the second thing is also that among the model configurations, the impact is different. For example, if you look at the first one or the second one, the 6th or the 9th model configuration or row, then you see that the impact of temperature is much lower than in some of the others. So this just means that these configurations are more driven by plankton and the others are more driven by temperature. Próximo, por favor. Yeah, then I'm fitting location also, distribution. In the model, you can see on the left part, that's the historical period. And you can see the model fitted to the data, which is the center of gravity on the latitudinal axis of the stock. So the first line gives that for the early life stages where they're spawning. The second line gives that for the adult population. And it's a bit different here because for the adult population, I took the range. There's not so much data available for some of the habitat, so it wasn't enough data. So what I'm using here is the range of different model parameters in response to where they migrate to the best food and how far that migration distance is. And the range you see here is the range of these different model configurations. And at the bottom row, you can see the distance to coast on the other axis, on the longitudinal axis, which has also been fitted to data in response to upwelling strength. And then you see how the variability of this is projected into the future. Próximo slide. So these are the population trajectories. In the first row, you can see the abundance of the stock. In the second row, you see the reproduction. That's the number of eggs produced per adult. And in the bottom row, you see the early life stage survival. That's the number of recruits per number of eggs. So firstly, you see that there's a general recovery of the sardine population. Then in GFDL, that is a bit more limited by the food availability and by the slower warming rates. And in Hadley and IPSL, that the population reaches pretty high levels, up to the historically high levels that were in the 1930s. Because the warmer temperatures lead to high early life stage survival. And later in the projection, there's some limitation by adult food availability. And the gray area you see there, so the colored area is the range of the ecological model configurations. And the gray area is the thermal uncertainty, which I just explained. And you can see that after about the second half and the later third of the century, the thermal uncertainty dominates the uncertainty range. And also that there are some decadal scale fluctuations produced. So different model configurations kind of, some have more fluctuations, some have less fluctuations, but they mostly agree on the timing of the fluctuations. So they're not all over the place, but they're basically, there's certain periods when they all go up, but just to different levels. And if you look at the bottom and the center rows, you can see a little bit of the reason for that. In the bottom row, you see the early life stage survival. And you can see that there are periods when early life stage survival is very high because they're good temperature and good food availability for early life stages. And that usually coincides with the rates in the population. And you can see in the middle row that also there's periods when egg production is higher because adults have a high amount of food. And if both coincide, you usually get an increase on the population, but you can also see in the center row that in general, there's a decrease in egg production. These are density dependent effects mostly, but also decreases in adult food availability. while you see that at the bottom row, there's a general increase in early life stage survival. Another interesting thing to see is that the fluctuation of these things has a different periodicity. So that if you look at early life stage survival, it's mostly like 1 to 3 years that this is fluctuating. Reproduction is fluctuating a bit slower. It's more like 3 to 7 years or something. And these two things in combination are enough to cause the slower fluctuations in the population. So this can explain these boom and bust cycles basically to some extent. Proxima slide. This is again the distribution on the north-south axis. So this the same thing, but integrated over 20-year intervals. And it shows you how it's moving north. So the population is moving north in response to temperature. And for the upper row is the adult feeding population, and the lower row is the spawning habitat, the life stages. And you can see that the spawning habitat, because in the model it responds to temperature, it's moving north at a faster rate than the feeding habitat. And the feeding habitat, assuming that they go where the best food is, that habitat for the best food that doesn't move north quite as fast as the temperature habitat. So if you're looking at the whole where the whole stock moves, that means that the total shift will be less than if you're extrapolating just based on physical parameters and just assuming that they stay where the best physical habitat is. Proxima slide. So the model has the fisheries catches in it also. So these are the landings, and for the past, this is fitted also for the total landings data and the landings at age. And then there's two different fleets. So there's a northern fleet in the Pacific Northwest. That's what's given in the bottom row here, and there's a southern fleet in California and northern Mexico. And I'm also looking at the distribution between these two different fleets. And for the future, I'm assuming that the total catch is based basically on the historical relation, on the exploitation rate that we've seen in the calibration period. So basically, based on the stock in the past year, then the quota is set for the next year. So the landings are proportional to that. So that's why the landings here in the forecast are basically like a smoothed proportional version of the biomass. But the shift that you can see in the bottom row depends on the position of the stock in the model. So as it moves further north, you can see there's a lot of interannual variability, but the trend goes slightly up, and it reaches about half of the catch for the northern fleet, up from 20 to 25%. Next slide, Proxima slide. And this gives an overview over all the different model configurations at all different overthermal sensitivity and over the ecological sensitivity, and during 20-year intervals also. Just to show again the same point, basically, that the chance for high sardine stock increases mostly under the warming because of the better recruitment. But there's also the risk for having a very low stock, for having stock collapses, increases also slightly later in the projections, especially under the fast warming ones. Proxima slide, Bobo. Yeah, so this was sardine. I'm going to show you the adaptation for anchovy. Proxima slide, Bobo. So I took the same model and I adjusted some of the characteristics, life history characteristics, and refitted the spawning and feeding location. And the problem here is that we don't have a good stock assessment that goes back so far, because the abundance has been low and the stock has been low. So there was the stock assessment had just started this year. goes a few years back, and there's not enough reliable data, but there's other data sources. There's an estimate of biomass based on egg production, and there's some diet time series of sea lions, of California sea lions, and I'm using these data sources to fit the model for anchovy. I'm also using an updated ROMS Numero hindcast that goes on to 2019 to fit this model, and have some preliminary results on this. It shows that roughly reduces, as you can see here, reduces the biomass and the fluctuations. There's some higher peaks, some outliers basically there, but it's in discussion if these are actual data points or if they're biases because of movement of the population, where basically the survey has overestimated the population. But in any case, the model also captures the decrease during 2009 to 2015, the very low stock that we've seen, and some of the increases in the last few years. Proxima slide. So as I said, this kind of preliminary, I'm not considering fisheries here yet, but there hasn't hardly been any fisheries. There's been some between 1980 and 1990, and I'm not considering it for the future. And also haven't done the detailed sensitivity analysis for the thermal response yet, but I've done some initial checks that this is not caused by the limitation in the early life stages. So you can see that there's some periods where there's good biomass in anchovy. In the GFDL model, it's kind of in the 2050s and early on. And the Hadley and IPSL models, there are periods, there's more short-term fluctuation here, and there's some longer-term variability, but also because that's not in the calibration period, that's probably why it's not reproduced in to the same extent as for sardine. So there's periods with solid biomass, but there's not a high recovery, and there's nothing like a change back from sardine to anchovy or something like that. Proxima slide. So the same as before. So you see eggs per biomass, the reproduction, and the recruits per egg, the early life stage survival, and the second and third row here. And you can see that the decreasing availability of food kind of inhibits the egg production. That's part of the failure of the recovery, because actually the recruitment success isn't so bad. There's still good periods with good recruitment success. So that's not the reason for this failure in recovery. Proximal. And this is again the overview for the stock. You can see that the stock-related risk is increasing under all three models, especially under GFDL. So the percentage of model configurations that are below the collapsed stock threshold, what we would consider that, is decreasing in the future for anchovy. Proxima slide, Propo. Yeah, this is it. Just as a summary and as a conclusions, using the downscaled Earth system models from the regional models and biogeochemical models, we can actually explain the boom and bust cycles that we've seen, the last cycle in the 90s and the 2000s in the California current. And we also can reproduce decadal scale fluctuations in the future projections. And these are driven by a combination of the environmental drivers, the temperature experienced by the early life stages, the food availability and for the early life stages and for adults. But they're also modulated by things that are going on in the population, by feedbacks under changes in age structure, by density-dependent consumption, migration, and also fisheries. So if you consider these both different things, the environmental parameters and the population feedbacks, I think it's possible to forecast and project boom and bust and small pelagic fish populations. And yeah, we've seen that sardine will likely recover by mid-century under the different, dependent on the different Earth system models. And I haven't found any indications for lasting resurgence in anchovy. And but these projections have different uncertainties. One is that the Earth system models lead to diverging trajectories, and the timing and the factors that are limiting are different between the different Earth system models. Then there's ecological uncertainty, so the contribution of different population processes and feedbacks. And this is the dominant part of uncertainty in the midterm, 20 to 50 years. But we could constrain that further when we get more information on biological rates. And then in the long term, the dominant part of uncertainty is thermal window uncertainty. That's the unknown optimum for survival of physiological optimum and limit for survival of early life stages. And in the long term, longer than about 60 or 70 years, especially in the fast warming models, that's what dominates uncertainty. Próximo, por favor. Okay, thank you very much. These are my contributors who have helped me with this work, and you can see the sardine part has just been published in ICES journal, and the anchovy part is in the works. Muchas gracias. Si tienen algunas dudas, pueden preguntar. Gracias.
Bueno, muchas gracias, Stefan, por esta excelente presentación. Entonces, estaríamos atentos a las preguntas que pueden ser, pueden escribirlas en el chat o si desean pueden pedir la palabra. Quizá podría empezar yo. I would start, Stefan. Can I do it in Spanish or you prefer it in English?
I will try.
Okay, well, I will give the translation after. La pregunta es, ¿cómo digamos, se comparan estas proyecciones en relación a lo que ya está establecido en general en la comunidad científica del desplazamiento de los centros de upwelling hacia los polos? O sea, my question is, in which extent your results agree or are consistent with these projections of the poleward displacements of the upwelling systems in the global ocean? So is this what your results are according to this hypothesis or not?
Yes, I think they agree. Sí, creo que están de acuerdo con esta hipótesis. En el Corriente de California también vemos un cambio, un movimiento de la zona de afloramiento hacia el norte. Y este efecto del movimiento es más pronunciado que el cambio total de la fuerza del afloramiento. Y eso tiene diferentes efectos en las poblaciones de pesca. En mi modelo, el efecto que tiene es que la zona de temperatura óptima para el spawning, para las larvas, se mueve hacia el norte, y también la zona del prey, la zona de la presa, de la mejor cantidad de presas para la consumpción del stock, también se mueve hacia el norte. Y también está conectado al afloramiento por la distribución de nutrientes y otros factores.
Okay, but nevertheless, in terms of the responses by the two species, for example, in the case of anchovy, the projections do not show an upward trend of the biomass, that they will keep at the low level. Mi pregunta es en relación a que, o sea, si bien es cierto, hay un desplazamiento hacia el polo del alimento y esto, bueno, se observa en las proyecciones de los modelos. Sin embargo, a nivel específico, en el caso de la anchoveta de California, de acuerdo a las proyecciones, esta se mantendría en niveles bajos, ¿no? La sardina estaría siendo beneficiada, es lo que entendí, pero la anchoveta no.
Sí, es correcto. I will do this in English. I think it's easier for me.
Yeah.
So this is linked to the information we have available from the calibration period. This is also a bit more limited for anchovy because it has been relatively low during the whole calibration period, 1980 to 2019, that we have used. If we had data that went further back during the last period of high anchovy, maybe we would have more information on this. But within the calibration period, there was running a lot of looking for different model configurations. There was no model configuration that fits the past historical period and still responds with an increase in the future, if that makes sense. So in contrast to sardine, where we've found this, we've found a lot of contrasting responses, and we've found most of the responses are positive and show that it's an upward trend, which is because of the positive correlation with temperature, mostly the warming. For anchovy, there was no such model configuration. But as I also put, this is kind of a preliminary result because I'm more looking into the diet data, and I'm looking for more model configurations that could have different, that fit better the amount of anchovy we see represented in the sea lion diet, because the estimate of biomass based on the egg surveys that are there could be biased. They're not very reliable. They're not as good as a stock assessment.
Okay, I will try to summarize your response to the colleagues. Bueno, con respecto a la respuesta que se observa en la anchoveta en las proyecciones futuras, posiblemente esto podría estar influido por el periodo corto de configuración del modelo, ¿no? Conforme lo explicó, el periodo histórico, digamos, en el cual se basa la configuración del modelo para la sardina es mucho más largo, ¿no? Mucho más completo que en el caso de la anchoveta, que solamente son un par de décadas, ¿no? Entonces, esto puede, digamos, de algún modo haber limitado las proyecciones que se obtienen con respecto a la anchoveta. No, so what I'm saying is that maybe the short period of configuration, the short period of reference for building the configuration of the anchovy model could have influenced on the projections that you are obtaining at this point. Does it make sense? Is that a good summary of what you said?
Yeah, that's a good summary. It's a bit more general, maybe like the lower data availability. So I think the points that we have, data availability is lower because the stock was so low. So uncertainty relative to that data we have is just higher. Yeah.
Uh-huh. Uh-huh. El periodo utilizado es un periodo en el cual la anchoveta ha estado en niveles muy bajos y la incertidumbre pues también es más alta, ¿no? Entonces esto se refleja en las proyecciones que se obtienen. Okay, there is a question in the chat. The question it says, si podría explicar el mecanismo de cómo la temperatura afecta al individuo, curvas de temperatura y su efecto en la fisiología. If you could explain the mechanism by which the temperature affects at the individual level, for example, the temperature curves and their effect on the physiology.
Yeah, so the temperature effect that I have here in the model is on the early life stages, on the larvae, and this is based on what we see in experiments. What we usually see is this thermal response curve that I show. So it's usually an increase until a certain point, then there's an optimum, and then there's a steeper decrease in survival. And there's papers that show that this linked to two things. It's linked to thermal stress that leads to higher mortality, but it's also linked to the positive effect is linked to faster development. And faster development usually leads to reduced mortality because their early life stage mortality is higher the earlier it is in the life, right? So they got to a stage where they have reduced mortality faster, and that increases total survival. That's the positive effect. But then that's until a certain limit, and then it decreases again because thermal stress gets too high. So that's what I'm incorporating here. And there's experimental data that fits these processes, and that shows that if you have larvae in tanks, in aquaculture tanks under different temperature, you see these curves emerge. And that's why I was assuming in this model this curve, and then assuming different and testing different positions of the thermal optimum under the thermal limit. And I get different curves for the early life stages, and I'm testing all the different curves in conjunction with the different effects of plankton in the model. But I'm considering the early life stages, and here at this point I'm not considering like the metabolic effects this has on adults, for example, and egg production maybe in adults or something. For the adults, I'm just considering the food availability.
Okay. So bien, bueno, básicamente se considera el efecto de la temperatura en las primeras etapas del ciclo de vida, ¿no? de los organismos, sea sardina o anchoveta, y básicamente se parte de un principio de que el efecto es no lineal, digamos. Habría una etapa, ¿no? donde el efecto es positivo, y eso está ligado a que un aumento de la temperatura conllevaría un crecimiento más rápido de las larvas, ¿no? Pero a partir de cierto punto, ¿no? el aumento de la temperatura generaría un estrés térmico sobre la fisiología de las larvas, ¿no? Entonces, por eso es de que en general la tipología de estas curvas de temperatura versus sobrevivencia de las primeras etapas de vida no tiene, digamos, como una ventana óptima, ¿verdad? Ahora, con respecto a los adultos, no se ha, digamos, considerado la temperatura, sino más bien la disponibilidad de alimento. That is what you said, right? That for the adults, you didn't explore the relationship with the temperature, but rather to food availability. Is that correct?
Yeah. Correct.
Okay.
Yeah, exactly. That's what. Maybe I will look into it. I'm thinking to have a more detailed energy budget in the future and compare that to other results from an individual-based model. But I haven't done it yet.
Ok. Bueno, Jorge fue el que hizo esta pregunta. No sé cuál Jorge es, pero si tienes alguna repregunta la puedes colocar, o si no la puedes decir directamente a Stefan. Mientras tanto ha llegado otra pregunta más. Esta pregunta es de Héctor Sarmiento. Dice, el modelo muestra una recuperación de la sardina a mediados del siglo, casi 30 años, el calentamiento global y la aceleración por el efecto invernadero. ¿Tienes información de la presencia de túnidos en las corrientes más importantes? Y si lo fuera, se tendría que activar el uso de las conserveras como alimento de primera línea. Gracias. Okay, so here what Hector says is that in fact the model shows this increase of the sardine until the mid of this century, and this is related with the global warming. But the question is if you have any information about the tunas, of the response of the tunas in these currents, and if that is the case, if a possibility would be to make cans for food, for cans for food based on the exploitation of tunics?
For the elementary use of tuna as canned food.
Yeah, that is the second part
right?
of the question. That is the second part of the question. The first part is if you have any information about the tunas in the same period.
I don't specifically work on tunas. Colleagues of mine do. They work mostly on the spatial distribution and on the distribution shift. So there's species distribution models showing that tunas basically will also follow the environmental parameters and move northwards, move polewards with the warming. But I don't think there are yet any like population models for tunas that are. The problem is that they're highly migratory species and they're just huge. They migrate over the whole Pacific. So it's way more challenging to model their populations. So I'm not aware of any like projections of biomass, of available biomass of tunas, and I'm not sure how that will impact alimentation and food availability.
Okay. Bueno, el doctor nos dice que él no trabaja específicamente con túnidos, pero conoce los resultados de las investigaciones de otros colegas suyos. Lo que, en general, la problemática con los atunes es de que, como son especies altamente migratorias, es difícil modelar su biomasa, ¿no? Entonces, es en general un poquito complicado poder proyectar sus cambios futuros, ¿no? Puesto que en realidad las respuestas son de gran escala. I don't know, Stefan, if you hear me, because your image is frozen now in my computer.
Oh, I hear you well.
Okay. Well, I just said that what you explained about the complexity of modeling tuna, because it's a very highly migratory species, and so it is not that easy to model its future behavior. Another question. This is from Jorge Flores. La voy a leer. Dice, se han realizado estudios de crecimiento de larvas en laboratorio en Perú, en el cual la anchoveta en Graulis ringens es favorecida por el aumento de temperaturas al menos hasta 19 grados centígrados. Más allá de esta temperatura hay incertidumbre. Esta condición podría indicar que esta especie, o sea, en Graulis ringens, podría adaptarse mejor al cambio climático comparada con las especies de California. Okay, well, Jorge Flores asks following. He says that there are some studies of growth of larvae made in the laboratory conditions in Peru, where they have found that the anchovy, the larvae of anchovy, are favored by the increase of the temperatures at least until 19 degrees Celsius. But beyond 19 degrees Celsius, there is a high degree of uncertainty. The question is if this condition may indicate that this species, Graulis ringens, would be better adapted to climate change as compared with the California species.
That's a very interesting result and a good question. For sardine, what I've mostly been focusing so far, I think the optimum temperatures usually been found around 17 degrees. So yes, I guess that would mean that the temperature effect could be more positive for the Peruvian anchoveta in the future. But obviously this always goes together with the other effects, with the effect of changes in upwelling and changes in food availability. So you would have to consider everything together to see the outcome under climate change in the Peruvian system.
Okay, it's just a clarification. You said that the thermal optimum for sardine is 13 degrees Celsius?
17.
17, okay. Bien, entonces la respuesta es de que efectivamente para el caso de la sardina, por ejemplo, en el caso de California, las temperaturas, el rango de temperaturas óptimas está alrededor de los 17 grados, ¿no? Eh, entonces, en el sentido de que aparentemente la anchoveta de Perú tiene una mejor tolerancia a temperaturas cálidas, ¿no? Esto podría darle una mayor capacidad adaptativa con respecto al calentamiento que las especies análogas en el caso de la Corriente de California, pero además hay que considerar los otros procesos, ¿no? Como la disponibilidad de alimento, las tasas de afloramiento, etc. Okay. ¿Alguna otra pregunta más? Pueden hacerla directamente si desean, pidiendo la palabra y hacerla directamente a Stefan, o si no, si prefieren, pueden escribirla. Pueden hacerla en inglés también si desean directamente y trataremos de traducir a todos.
Dimitri.
Sí.
Hola.
Hola.
Luis Escudero. First, I will try to make my question in English. First of all, I would like to say to Stefan, a nice presentation. I can be present from the beginning of the presentation, but I want to know, in your conclusions, you said about the model, it don't include the fishing effort of the sardine, just put only temperature.
I'm sorry, can you repeat that? It doesn't include what for
Fishing
the sardine?
effort.
Oh, the fishing effort. Yes, it does include the fishing effort. Yeah.
Oh, sorry.
And
yes, sorry. And the second part is about the recovery of the sardine, because we are waiting more than 20 years for this, and don't see this. Sorry.
You're not seeing the recovery of sardine in the Peruvian system?
Yep.
Yeah, I think my knowledge of the Peruvian system, I have worked a little bit in the Peruvian system, but it's been a few years. I think I would have to get updated. I don't have updated information. I think the habitat is different. So the upwelling system functions a little bit differently. And anchoveta has always been much more important in the Peruvian system than sardine. And it was kind of, for the last decades, it was the other way around in the Californian system. So I think the niches, the ecological niches in the system are different, and you can't make a one-to-one comparison. It would be very interesting to look at that in more detail and look at the available data. And I'm not sure what, for example, for adults and for larvae and exolarvae and sardine is available. I'm not sure if that could be used to look more into if a recovery is possible or likely, because the mechanisms might be different. I wouldn't assume that the mechanisms that lead to recovery or collapse are the same in both systems. I think they can be different. Hope that answers your question a little bit.
Okay. I can try to translate that for the other people. Lucho, si deseas, puedo tratar de traducir lo que ha dicho Stefan para el resto, ¿sí? Bueno, la respuesta es de que si bien él no está familiarizado, digamos, con la problemática de la anchoveta y la sardina en Perú, lo que sí se conoce es de que en general el sistema de afloramiento de Perú siempre, digamos, ha tendido a favorecer mucho más a la anchoveta que a la sardina, mientras que más bien tiende a funcionar al revés en la Corriente de California. Entonces, los sistemas desde el punto de vista físico tampoco funcionan exactamente igual, ¿no? Puede ser que haya otros procesos involucrados por ejemplo, en la sobrevivencia de los primeros estados de vida de la anchoveta y la sardina de Perú con respecto a los de la Corriente de California. Entonces, habría que mirar con más detalle, ¿no?, esas características ecológicas de las primeras etapas de vida en relación a las condiciones físico-químicas, como para poder tener mayores elementos y explicar, digamos, esta ausencia, ¿no?, o limitada abundancia de la sardina que vemos frente a Perú ya desde hace varias décadas.
Gracias.
Welcome. ¿Alguna otra pregunta, por favor? Quizás los colegas que trabajan con el modelamiento numérico en Delimarpe de pronto tienen alguna pregunta, la pueden hacer verbalmente o por el chat de la reunión. Okay, maybe I can have another question, Stefan, is about the outcome of this project, Future Seas 1 and 2. Obviously, the results that you're obtaining are quite important for management, and I guess for the decision makers, but in a strategic time scale, because it's not for the year-to-year management, but for the next decades. So I'm curious about if your project has stakeholders from the industries or from the government that are implied, and in which way you are delivering this information to these stakeholders. Mi pregunta es, considerando la importancia de los resultados de estos estudios para el manejo, o sea, si el proyecto del cual proviene este estudio involucra la participación de actores de interés de la industria o del Estado, y de qué manera están trasladando este tipo de resultados a esos actores de interés.
Yeah, we're actually doing that. We actually had a meeting with stakeholders just last week. So this included fisheries associations, processing facilities, and actual fishers going out, and we presented the results of this model and of other models. So it's an interdisciplinary project, and there's a part of the project looking at management strategy evaluation. And this is where they're actually testing different harvest control rules, different actions to set quota and other things, and their effect on the catches and on the biomass. So part of my model work, as you said very correctly, it's more like a mid and long-term assessment. I'm not trying to make a forecast over the next 1 or 2 or 3 years, but it's more like a trend. So part of this goes into this management strategy evaluation, and so that is, for example, the input of recruitment variability that I produced with my model goes into the variation that goes into it's being tested, what that variability has, what kind of impact it has on the stock assessment models, and if these models are what's the best way to use these models, and if other harvest control rules can be better. And I'm also working on this in my model, because for sardine, the harvest control rule for sardine has a temperature factor in it, and I'm testing different rules. And then, excuse me, since I have different the fisheries exploitation in my model, I can just change the exploitation. And that's another thing that I'm working on, to see if there are other rules, maybe not on temperature, maybe based on plankton, or also considering the location of the stock. If there are other easy rules that are more robust and can serve to have both a better stock and optimize landings at the same time, while having like security of not causing collapses. And that's obviously something that the stakeholders are very interested in. Yeah, but as I said, also it's like a long-term strategic work that we will continue next year. And also in an upcoming, there will be just last thing to add, there will be an extension of the project that hopefully will come, that we've applied for, that will look more into the impacts on fleets and continue the work with the stakeholders.
So do you mean, just to clarify, so do you mean that beyond the results related with the projections, which are important by themselves, but which correspond to longer time scales than the day-to-day management, your approach using these effects of temperature on the early larval stages, or the food availability and adults, this kind of knowledge that you are generating by using different configurations or different tests are also useful for improving the harvest control rules. And actually this knowledge could be applied not only thinking on the long term, but also in the current management process. Is that what you meant?
Yes, that's exactly what it is. It's the quantification of uncertainty that I get from my projections. That's something that's very relevant for the management process, and that's something that's feeding into this MSE work.
Okay. Bien, bueno, lo comenta Stefan es de que, bueno, efectivamente hay bastante participación y comunicación con los actores de interés de industria, del Estado, relacionados con este proyecto. Justamente en la semana anterior hubo una reunión con los stakeholders, o sea, con los actores de interés, donde se presentaron, entre otros, los resultados de este estudio. Lógicamente, además de la importancia, ¿no? Un poco estratégica, digamos, de lo que indican estas proyecciones en relación a la evolución de los recursos en las próximas décadas, ¿no? Hay, de todas maneras, una contribución ya de por sí para el proceso del manejo, por ejemplo, a través de la cuantificación de la incertidumbre, que es algo que, digamos, se ha desarrollado en el contexto del estudio, que justamente hemos visto hoy día, o también a través de, o a partir de los tests, ¿no? y experimentos numéricos, ¿no? de la relación de la temperatura con las primeras etapas de vida que finalmente influyen en el reclutamiento, ¿no? Digamos, todos este conocimiento nuevo generado tiene importancia porque puede enriquecer, ¿no? los procesos de manejo y también las reglas de control de la cosecha, ¿no? Implicadas en el manejo de la anchoveta y la sardina en la Corriente de California. Okay, well, maybe this is the last question. Hay una pregunta que creo que sería la última, de Héctor Sarmiento nuevamente, donde nos pregunta, es una pregunta un poco más general, acerca del efecto del carbono en los océanos. ¿Variará o cambiará la productividad del afloramiento en las corrientes más importantes? Well, there is a rather general question that is written in the chat, and it's about the productivity of the boiling systems. The question is if, what I understand is if the effect of the carbon absorption by the oceans related with climate change would vary or change the productivity of the upwelling systems or the main upwelling systems in the global ocean?
Yes, I understand the question in a way that it's about the surface CO2, the anthropogenic CO2 that's taken up and leads to acidification, right?
Yeah, that's what I understood as well.
Yeah, so I think that's upwelling systems are a bit special cases here, because I think the CO2 in upwelling systems is not mainly driven by the surface uptake, but it's in the source waters and then the biological productivity within the system, and maybe just the surface waters are impacted by acidification, and mostly in most upwelling influenced areas, the CO2 will mostly be driven by upwelling activity and not so much by the uptake. But I'm sure there's areas which are maybe not so much upwelling activity driven where that can have an impact. Yes, but it's maybe then not so much on the lower level productivity, but maybe it's more on specific organism that either live on very coastal habitats or on very in different habitats.
Okay, thank you. Sí, entendemos la pregunta en relación a la absorción del CO2, ¿no? Que está relacionado con el proceso de acidificación. Bueno, este es un proceso que ocurre básicamente en la capa superficial, pero en general, ¿no? Es mucho más importante la dinámica del carbono relacionada con la productividad misma del afloramiento y con la intensidad de ¿no? Que tiene que ver con las tasas de upwelling, ¿no? Las tasas de afloramiento, ¿no? Y las aguas fuente, digamos, de estos procesos, ¿no? Que ocurren en los sistemas de afloramiento. Entonces, en general, se podría decir de que el impacto, ¿no? De la absorción de CO2 en la capa superficial no sería, digamos, de primer orden, ¿no? Para los sistemas de afloramiento, puesto que su productividad está más relacionada con la dinámica misma de estos sistemas, ¿no? Las características de sus aguas fuente, ¿no? Y bueno, la intensidad de las tasas de afloramiento. No sé si hay alguna pregunta final o adicional. Yo me parece que, entonces, I'm asking if there is an additional question. I think we had several of them. Bueno, entonces muchas gracias, Stefan, por esta muy buena presentación. Realmente creo que es bastante inspiradora para los estudios que también venimos llevando a cabo en IMARPE sobre el modelamiento, ¿no? Futuro, presente y futuro en realidad, de los procesos de reclutamiento, crecimiento y poblacionales de la anchoveta principalmente en nuestro sistema. Así que imagino de que de todas maneras vamos a seguir en contacto contigo para intercambiar ideas y experiencias en relación a lo que venimos haciendo acá, ¿no? Y la estrategia y el enfoque que tú vienes aplicando. Well, thank you, Stefan, a lot for your presentation. I think it has been very inspiring. Of course, there's a lot of interest from us because, as you know, here in IMARPE, we are also looking at modeling the ecology of anchovy and their early life stages in the present and in the future. And I think your approach is very interesting, and I'm sure that we will continue in touch with you in order to exchange ideas, discussions, and so on. And so thank you again. I don't know if you want to say any additional words.
Yeah, thank you too. Muchas gracias por la invitación, por las preguntas y el interés. Y si hay más dudas, más preguntas, me pueden escribir un correo electrónico también. La dirección está en la página web de Universidad de California o el NOAA. Yeah, thank you very much. I'm gonna voy a practicar mi español un poco más. Tal vez la próxima vez puedo dar la presentación en español. Muchas gracias.
Bien, gracias, Stefan. Bueno, y gracias a todos por su participación. Entonces nos despedimos por el día de hoy y esperamos poder repetir otros webinars también con otros expertos internacionales, así como Stefan el día de hoy. Hasta luego.